Hello and good to see you back. In this session, we will cover the practical aspects of sequential excavation and the new Austrian tunneling method, popularly known as NATM tunneling. Sequential excavation method is generally known as the new Austrian tunneling method, NATM, NATM. It is primarily used in poor and weak rocks and soils. The mechanized excavation and the drill and blast excavation are methods based on techniques of cutting and breaking the rocks. Sequential excavation method, on the other hand, is an excavation process. In sequential excavation method, the rock cutting and the breaking can be by means of machine and blasting. The practical essence of the sequential excavation method is an excavation procedure combining small section excavation and temporary supporting, and then to form a full opening. As pointed out by Professor E.T. Brown, NATM can refer to both a design philosophy and an excavation method. NATM's approach is to deliberately mobilize the strength of the ground around the tunnel to the maximum extent possible. Mobilization of ground strength is achieved by allowing controlled deformation of the ground. Therefore, the ground will need minimum support requirement. Primary support of the ground is installed having load deformation characteristics appropriate to the ground condition, and the installation is timed with respect to ground deformation. Instrumentation is installed to monitor deformations in the primary support system, as well as to form the basis of varying the support design and the sequence of excavation. NATM, as an excavation method, involves the following excavation steps. First, tunnel is divided into sections, sequentially excavated and supported with primary support. The primary support is closely monitored and modified if required. Finally, sections are opened up to form a full tunnel. Second, primary or initial ground support is provided by fiber reinforced shotcrete, steel arch, lattice girders, bolts, and wire mesh. Adequacy of the support is closely monitored and modified. Thirdly, after full opening up of the tunnel, permanent support is applied, usually, but not always, by cast-in-place concrete lining. As I mentioned earlier, the design philosophy of NATM is to support the ground to match the ground conditions and ground pressure deformation characteristics. Isn't that familiar? We learned in ground support interaction concept that support design in weak and poor rock mass is to balance the ground and the support by mobilizing supported pressure and limiting the ground deformation. Yes, in that sense, ground support interaction concept is the theoretical basis of NATM design. In describing NATM as an excavation method, we mentioned that it involves the steps of sequential excavation and monitoring. The table here provides a summary of those excavation steps and activities. First, the tunnel is divided into sections, usually left-right symmetrical. Excavation is started with one section. Because of generally weak and poor ground, excavation is by excavators and machines. Second, the excavated section is temporarily supported, usually by installing quickly the support elements such as shotcrete, lattice girders, wire mesh, and bolts to form a closed ring. Using shotcrete as a quick support and form a closed support ring are key features of NATM and were highlighted by its inventor, Professor Rubeswick. Third, systematic instrumentation monitoring are conducted to observe support load and deformation to ensure the ground stabilizing. If ground is not stabilizing, additional support will be added. Systematic deformation monitoring is another highlighted feature in NATM. With one section is advancing, then the steps are repeated to excavate the next section. Repeat the step 1 to 3 to excavation all the sections of the tunnel. The last step is to remove all the internal support between the sections, open up the full face of tunnel, and install cast-in concrete lining as a final lining. The NATM excavation processes and advancing cycle can be explained by this illustration. The tunnel is divided into 4 sections. Excavation started with the first section, side drift 1 in yellow. The section is supported with a closed rim and the ground deformation is monitored. At some distance behind, the second section, side drift 2 in green, is excavated, supported, and monitored. It is followed by core 1 in red and the core 2 in blue. After all the sections completed, the support element internally are removed. The full tunnel in purple is then supported and with final cast-in concrete lining. Let me show you a couple of examples of sequential excavation processes, particularly on excavation and temporary support. This is a rather typical way to divide the tunnels into 4 sections. Excavation sections are small and the shape allows to form a closed ring, so the support can be effective. With relative low strength, rocks are excavated by machines, for example, excavator and load headers. Here you can see the excavation sections and the temporary support for those sections. The sections are in small, supportable shape and size. The supports are quickly applied to each section after excavation in the form of a closed load-bearing ring by shotcrete, reinforced by steel fiber, and perhaps with lattice girders and other support elements. Here are some practical guidelines on excavation sequence. Length of each excavation round is limited to 1 meter. The maximum unsupported ground is 1 meter on the roof. The invert should be supported to form a closed ring within 5 meters. Advance rate should be kept at 4 meters a day. This is to allow the shotcrete to gain sufficient strength. Ground level must be lowered below the tunnel level. If in very poor ground, the excavation phase can be stabilized by shotcrete, glass fiber bolts, and pre-grouting, so on. The design of initial and primary supports is based on the ground condition and the ground pressure deformation characteristics. As we mentioned earlier, it uses the ground support interaction concept. To obtain the ground support deformation curve and the interacted deformation curve for NATM design, numerical modeling are commonly used. Physical experiments and measurements, empirical methods such as rock mass classification system can also be used. The support design is verified by monitoring and can be adjusted with monitoring results. NATM sometimes is also referred as sequential excavation observation method. Observation of ground behavior through monitoring plays a key role in sequential excavation. Instrumentation and monitoring are performed primarily on ground displacement around tunnel using borehole extensometers, tunnel opening closure by measuring convergence, induced surface settlements by surveying the ground surface, and the bearing load of primary support by pressure cells and strain gauges. Some of the common instrumentations and monitoring techniques are shown in the drawing on the right. We will in fact cover more details on on-the-ground instrumentation and monitoring in a later session. Observation and monitoring is to ensure the support is sufficient and the deformation is under control during the excavation, as outlined in the ground support interaction analysis. Final concrete lining is usually cast-in concrete lining, but could also be precast concrete lining, installed when the following conditions are achieved. 1. Tunnel convergence are approaching stabilization, with side convergence is less than 0.1 millimeter a day, and the roof convergence less than 0.1 millimeter a day. 2. Tunnel deformation has gone through more than 90% of the total expected deformation. Therefore, the ground has basically stabilized under the primary support. The final lining is often not considered as load-carrying structure. It is more for the final cosmetic of the tunnel. In general, people recognize that NATM has advantages when appropriate design procedures are employed. For design, the excavation sequence and the support, NATM needs accurate ground characteristics and the ground support interaction curves. This today is primarily achieved by numerical modeling. Support monitoring and close observation is key activities in this excavation method. Time to react and time optimization is critical. NATM, because it allows ground to deform in order to minimize the support requirement. It also means that it will have relatively large ground deformation around the tunnel, and in turn may have relatively large surface settlement. Let us recapture this table showed at the beginning when we start covering excavation methods in session 4.7. We have 4 rock excavation methods by process. Full face excavation using TBM or drill and blast, and then multiple phase excavation for large section excavation are mainly for competent rocks as traditional hard rock excavation. Sequential excavation or NATM is for weak and poor rocks. For weak and poor rocks, full face excavation is also possible. Sometimes may be desirable by preconditioning ahead of the excavation so the ground may be stable enough for large span excavation. This is the preconditioned full face excavation, the third method mentioned in the table. Preconditioned full face excavation method in weak rocks is very briefly described here. Before excavation, the ground around the tunnel, particularly above the roof, in front of the excavation phase, are conditioned through ground improvements and ground reinforcements using fiberglass, full pouring, grouting, dewatering, freezing, and other techniques. With those preconditioning techniques, the weak and the poor rocks are strengthened and stabilized, and can allow for full face excavation of up to 80 square meters. Full face excavation generally leads to relatively high advance rate. However, it may require extensive and expensive ground improvements and reinforcements. Here is the end of underground excavation method. Next session will be on rock reinforcements and support methods. Goodbye and see you at the next session soon.